Suppose that you are responsible for making arrangements for a business convention. Because of budget cuts due to the recent recession, you have been charged with choosing a city for the convention that has the least expensive hotel rooms. You have narrowed your choice to Cincinnati and Nashville. Data on the prices of rooms of both cities was sampled. A sample of 35 homes in Cincinnati gave a sample mean of $91.71 per room, with a standard deviation of $20. A sample of 40 rooms in Nashville gave a sample mean of $103.02 per room, with a standard deviation of $25. Is there proof that rooms in Cincinnati are cheaper? Use alpha equal to 0.05 to test. Okay, this is a little bit different than the problems we've worked in the past, in the sense that there appears to be two populations in this one, and I'm asked to compare these two populations. So let me set this problem up. I'm going to let population 1 be equal to hotel rooms in Cincinnati, and population 2 be hotel rooms in Nashville. Now, what am I interested in about these hotel rooms? I want to compare the mean prices. So I'm going to let mu1 be the population mean price of hotel rooms in Cincinnati. The population mean price of hotel rooms in Cincinnati. And mu2 be the population mean price of hotel rooms in Nashville. Now, I've collected two samples. One sample of 35 hotel rooms in Cincinnati and another sample of 40 hotel rooms in Nashville. And I've collected some statistics from those samples. My point estimates of mu1 and mu2 are x1 bar, which is 9171, and x2 bar, which is 103.02, respectively. So my estimate of the mean price of hotel rooms in Cincinnati is $91.71, and my mean price of hotel rooms in Nashville, my estimate of that mean price, is $103.02. Also, the standard deviation was collected for each one. And notice that I'm subscripting these to keep track of them so I know which population they belong to. And my sample sizes were 35 and 40. Now, what I'm interested in doing is to try to see if this sample evidence, this $91.71 and $103.02, is strong enough evidence to say that mu1 is less than mu2, that the average price of hotel rooms in Cincinnati is less than the average price of hotel rooms in Nashville. Is my sample evidence strong enough to conclude that? I'm going to have to run a hypothesis test to do it. Now remember, when you set up a hypothesis test, whatever you are trying to prove is the alternative hypothesis. Now I'm trying to prove that mu1 is less than mu2. I have evidence to do that. What will I assume? I'll assume that mu1 is greater than or equal to mu2 and see if I can reject that. Now with the one population case, back in chapter 7, the procedure is pretty much the same. I'm setting up a null and alternative hypothesis. The alternative hypothesis or research hypothesis is most of the time what I have evidence to prove. The way we can write this, first of all, is we can say that trying to show that mu1 is less than mu2 is the same thing as showing that the difference between mu1 and mu2, where I'm taking mu1 subtract mu2, is less than 0. If mu1 minus mu2 is less than 0, in other words, it's negative, that must mean that mu1 is smaller than mu2. The reason it's written this way is because the sampling distribution of the differences in the sample means is normal. And we already have established a model for the normal distribution. The null then would be the opposite to that. So I'd say mu1 minus mu2 is greater than or equal to 0. Now, finally, the textbook, and this will be our first step of the hypothesis test, you would see it written this way. Mu1 minus mu2 equal to 0. The alternative is mu1 minus mu2 less than 0. Certainly, if I can prove that mu1 minus mu2 is less than 0, then I've proven that it can't be greater than 0. So I can just go ahead and assume that the null hypothesis is equal to. And one nice thing about that is that we can build the sampling distribution with 0 in the center. Assuming that the null hypothesis is true, our sampling distribution, and let me mark this, the sampling distribution of the difference of the sample means. And I'm assuming that the null is true, so if the null is true, they would be normally distributed around 0. The standard deviation given by the formula square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now we don't have the population standard deviations. We just have sample standard deviations, estimates of those population standard deviations. But the sample sizes are both greater than or equal to 30. So they're large enough that we can use the sample standard deviations to give us good estimates of the population standard deviations. So our standard deviation is approximately, and we're going to replace the population standard deviations with the sample standard deviations. And then for us, that would be the square root of 20 squared over 35 plus 25 squared over 40. And that turns out to be 5.20. Now, this is a lower tail test, so I'm going to set up a decision line with respect to my alpha at 0.05. And my z-value for that would be negative 1.645. And this is something we've learned before. Nothing's changed here. This is the large sample case, and we're going to use a standard normal. So there's only 2 or 3 of these values that we can just remember. That will be different than the t-distribution, which will be based on degrees of freedom. Our rejection region would start there at 1.645 standard deviations to the left, and then proceed down to negative infinity. So that would be our rejection region. So I can write a rejection rule. I could say reject h sub 0 if z is less than or equal to negative 1.645. And what z am I talking about? I'm talking about the test statistic. In this case, the formula for that would be x1 bar minus x2 bar minus d sub 0, in other words, what I'm testing against, divided by the standard error, in this case, using the sample standard deviations. So I'm going to plug values into that. 91.71, subtract 103.02. I'm going to take that difference, subtract what we're testing against is 0. We're assuming that there is no difference between the means, trying to see if we can prove there is. And then I'm going to divide by my calculated standard deviation. This value turns out to be negative 2.175. So this difference in the sample means a negative 11.5 3.1 is to the left of my decision line because its z-value is smaller, or to the left of the decision line's z-value. So I am far enough away from 0 to reject the null hypothesis. And I would conclude in step 5 to reject h sub 0 since negative 2.175 is less than or equal to negative 1.645. And I would conclude that mu1, right? I'm rejecting the null hypothesis, and I would conclude that mu1 minus mu2 is less than 0, which means that mu1 is less than mu2. And I would then say the mean price of hotel rooms in Cincinnati is less than the mean price of hotel rooms in Nashville. I have proven that Cincinnati's hotel rooms overall are cheaper than hotel rooms in Nashville. And I did this taking the test statistic and comparing it to my what the book would call the z sub 0.05 or z sub alpha value, which is the endpoint of my rejection interval. I'm over there in the rejection region. The difference in the sample means is far enough away from 0 to conclude that the difference in the population means can't be equal to 0. And in this case, the difference in the population means is less than 0. So with a sample of 35 hotel rooms from Cincinnati and 40 hotel rooms in Nashville, I'm able to conclude that the mean price of all hotel rooms in Cincinnati is less than the mean price of all hotel rooms in Nashville.